started. In the last class, we have discussed the relations between the moments at various points of the linkages. The same you can see on the board. This is where we have ended in the last class. Now, we will move ahead for determining the control system model for speed governor. Okay. So now, as seen in the last class, as we have obtained the relations between all these parameters, YA, YB, YC, and YD, and YE, where these do indicate the change in the moment, or what we call it as a displacement, at the point A, B, C, D, E, respectively. Now, I am converting this time domain functions into Laplace transforms for my easy calculation. So, converting them now, see, this equation will become delta YA of x is equal to Kc into delta Pc of x. This equation will become delta YD of x equal to K2 dash delta f of x. Then this equation will become delta YC of x is equal to minus K1 delta PC of x plus K2 delta f of x. Okay. And next is the fourth equation, which is delta YD of x, which is equal to K3 delta YC of x plus K4 into YE of x. And the last equation, delta YE of x is equal to minus K5. I do have an integral here. So I'll be getting 1 by s into delta YD of x. See, these are the expressions 1, 2, 3, 4, and 5 in terms of Laplace domain. Now, I am erasing all the remaining things. So these are the 5 expressions which represent the displacement at the points A, B, C, D, and E. Okay. Literally speaking, what are the inputs for my function now? Either I can manually change my power inlet, power intake, or this is an automatic control which is happening because of the change in frequency. These two are considered as inputs, which are going to affect my steam value setting. This is the actual steam value setting. As you have seen, at point E, I'm having this main piston of hydraulic amplifier, which controls the steam quantity to the turbine. So, I need YE in terms of PC and F. So, I'm going to get that equation now. Now, if you carefully see, so delta YE of x, I am rewriting this equation K5 by S into delta YD of x. What is YD? YD I already do have. Okay, I am neglecting these two terms because I may not need these things. So this is minus K5 by S into K3 delta YC of x plus K4 delta YE of x. Again, there is a YE, if you carefully see. So I am subjecting this one to here. So what I will be getting here? This one I will be getting here. So 1 plus K5 K4 by S is equal to minus K5 K3 by S into delta YC of. isn't it? Right? Now, what is delta YC of S? I have YC of S here, which is minus K1 delta PC of S plus K2 delta F of S. So I have employed all these terms. So I am eliminating, I am erasing these things. Okay. Now, simplifying this one. Okay. I am going to bring this minus K1 to outside. So this will become plus K1. Okay. Delta PC of S plus K2 by K1. Here you will get minus into delta F of S. Into delta of S. So now what is delta Y of S? I am going to bring this one to denominator here. So what I will be getting is K5, K3, K1 by K5, K4 plus into delta PC of S minus K2 by K1 delta F. This is my expression so for which I have obtained. Isn't it? Now, I am going to simplify it a little bit in order to get a one value here. So, say, in order to get one here, what I am doing. So, here I will be getting I have just rearranged the terms here. I have just rearranged my terms. Yes. Have you understood what I have written on the board? So this is what I'm going to get now. Isn't it? There must be some term here, I think, which I have missed here. Okay. So now, this I am treating it as a constant. So I am treating it as K is G. K is G. So this is time constant of my speed governor. This is 1 plus S into, this is time constant. This is gain of the speed governor. This is time constant of the speed governor into delta PC of S minus, I'll write this one as 1 by R. I'll define it shortly. See, this is the representation. This is the representation of a control system, in terms of control system. Now I'm going to write down here once again for you. I think in my last class I have forgotten here KC. Please check it. If there is a KC, I think there will be a KC here. Okay. Now see, delta YE of S is equal to K is G by 1 plus S into tau Sg into delta Pc of S minus 1 by R delta F. Okay, where Ksg is equal to K1, K3, Kc by K, and tau Sg is equal to 1 by K4, K5. And what is R? R is considered to be K1 by K. Okay, this is called as the gain of your speed governor. This is time constant of your speed governor, and this particular one is called as the speed regulation of the your governor, speed governor. Try to remember the thing. This is gain of the speed governor, time constant of the speed governor. This is regulation of your speed governor. Okay. Now, how to represent this one in a mathematical model? So, this is your mathematical model. This is your mathematical expression, right? This one. Now, converting it into a control system model. Now, I do have two inputs. One is delta Pc of S. The other one is delta F of S multiplied by 1 by R. This is delta F of S, which is multiplied by 1 by R. Both are to be summed. This is plus, this is minus. Okay, this is delta Pc of S minus 1 by R into delta F of S into so what is the output? Delta YE of S. This is the control system model. Okay. This is the control system model of a speed governor. Say that it is having two inputs. One is a manual power command, the other one is a change in frequency. This is a transfer function. Okay. Now we will see how to implement this one in MATLAB. Okay. Most of the times what happens is so let us simulate this model in a control system. So before going further, we need to have at least some values of Kc and this tau, isn't it? So normally these values of Kc and tau, you can choose on your own. Give me 1 minute of time before I open my MATLAB. Yeah. So before going for this MATLAB, I'll assume that my time constant of this speed governor, it will be very low when compared to my machine, because there is nothing, any component of IV mass. So I'm taking it as 0.5. And sorry, this is again I'm taking as 2. Time constant I'll be taking as 0.5. And speed regulation, generally you can take it as anything. I'm taking it as 3 here. You can take it as anywhere between up to 10 or 20 or whatever it may be. It is your speed regulation. Normally we will be having a speed regulation from 2 to 5. So now I'll be showing you 1 minute.
Now I'll be presenting to you how to simulate this model in MATLAB. Okay. And so now I'm presenting to you the simulation, MATLAB Simulink model of the developed model of speed Gardner. As you can see, uh, this is a Simulink library. Okay, so what the components which I do need? 1 minute. The components which I do need. The first one is I do need two inputs, so I'm taking them as a step inputs. So I'm taking them as a, you can find them in the sources. These are the two inputs. One, I'm naming it as CS, and naming it as S. So, and apart from this, if you see in the commonly used blocks, you can find a summer, and you also need a constant block because you do have 1 by r, right? So what I'll represent it as a gain, and the other one is a transfer function model. You can find that in this continuous. Here, if you can see, there are different types of continuous functions. So I am selecting a transfer function, and finally I am using a scope. This is my scope. So these are the components which are employing right now to study the model of speed Gardner. Now, if you carefully see, this is delta PC of S. Okay, so PC of S will be positive, whereas this one will be negative. This is negative. And this is my transfer function model. What is this one? Speed Gardner transfer function, isn't it? Right. So what I'll be getting, the output I'll be getting as y e of s, isn't it? So this is my output signal, isn't it? So what is this particular signal? This is my PC of S signal, right? What is this signal? This is f of s signal, okay? So I'm zooming it a little bit so that you can understand it well. I hope now you are able to see this one. Yes. Okay. So I'm giving two inputs. One is manual power command. The other one is automatic frequency. These are changes in power command. This is a change in frequency. I'm taking them as per unit values, and I'm giving as input to this one. Coming to the transfer function, as already been mentioned, it is KSG. As I already told you, I'm taking it as 2. In the denominator, the S will be having a coefficient of time constant. As I told you, the speed Gardner system will be having a very small time constant, so I'm taking it as 0.5. Okay. Okay. Now this is a speed regulation. As I already told you, it is going to be 1 by R. Okay. So 1 by 3 I am taking. Okay. Now I'll show you now. Here I'm changing the scope. Give me 1 minute of time. Yeah. Number of input ports is 3, and layout will be like this. Okay. So I want to see all the 3 inputs, and I want to see all the first one will be my power command input, the second one will be my frequency input, the third one will be my output. Okay. So I want to see all these things simultaneously. So I'll employ my I'll make it as a discrete one. Okay. And I will run this one for, let us suppose 0.2 seconds. Okay. Now let's gonna see what I'll be getting as an output. See, I have given a change in power command as 1, a change in frequency as 1. Now let us see what the change in the displacement is. These are all changes. Okay. Change in power command, change in frequency, and this is a change in steam valve setting. Okay. Now see, this is the change in power command is 1, PC of S, change in frequency is 1, see YE of S. Initially it was 0, there was no change in the setting, but there is see, as the time progresses on, there is a huge increase in the steam setting. Now let us run this one for, let us suppose, around 20 seconds. Okay, let's see what happens if it is being run for 20 seconds. Okay, see what I'm gonna get. It is getting stagnant at 2 seconds or so. It is getting saturated, isn't it? At a value of 1.33. Okay. So this will be your final steam setting, because there is a change in the manual command and also change in the frequency. So there's why there is a change in steam setting, and it is 1.5. 1.5 times the normal one. Okay. Now we will check different thing. Let us suppose there is no change in frequency. I'm setting it down to just 0. Okay. Now this is 0. There is only change in the power command. Now let's see how the system is going to respond. See, this is a system change. There is no change in the frequency. It is at 0. Change in power command is 1. See the change in YE of S. Isn't it? Now I'll keep this one as 0. And let's see what is the change. I'll take it as there is a 50% change in frequency. If there is a 50% increase in the frequency, if there is a 50% increase in the frequency, then it means that the speed has increased, right? If the speed has increased means demand has decreased. If demand has decreased means, as I explained in the last class, if demand has decreased, generation must be decreased. Generation decrease means steam input valve must be closed, isn't it? See, let's see. That's why what you are getting a negative value. Steam valve is being closed right now. That's why you are getting a negative thing, isn't it? So in this way, you will be having, yeah. Now I will show you what is the effect of this regulatory function. Okay. See, I have kept it as 3. Now if you see, okay, I'll run this one for 4 seconds. see, this is the effect of regulation constant of see, it is taking a settling time of 2. At 2 seconds, it is settling and to a final value of minus 0.32. Now let's see if I am going to vary this speed regulation. I'm going to vary this to 5. Let's see if it is going to have an impact of impact on the outputs. Yeah, see. Now if you carefully see, it is settling well below, well before 2. And see the final value also. It is somewhere around 0.2. Earlier, what was the value? Earlier, when we have kept 0.3, the value was 1.12. Now it is 0.2. So which means that the regulation, the higher the regulation, the higher the value of R, see, the higher will be the value of the steam setting. If R is increased, this value will be going down, isn't it? So this is one thing. Now we will see what is the effect of gain. Now let us suppose this is 2. I'll take it as 10. Now let's see what is the change. Now right now, without simulation, this is somewhere around 0.12 and is settling at 2 seconds, isn't it? Now let's see if I increase it the gain. See what is the thing? It is somewhere coming up to 0.58. Earlier it was somewhere around 0.52. Sorry, 0.12, isn't it? I hope settling time is same, but the magnitude is increasing. Okay. Similarly, if I vary the time constant, see, this is time constant. I am taking it as 0.2. If I vary the time constant, what is happening, you see? Earlier it was settling down at 2. Now it is settling down at 1 itself. So now you are supposed to explain me what is the effect of varying the time constant, the gain, and also the speed regulation on the characteristics of the speed. I have asked you in your assignment. Go through the assignment, try to solve it. I hope you have understood now how to solve the things using MATLAB. Okay. Thank you for joining, guys. In the next class, I'll explain to you the turbine model. Okay. Thank you once again.